we know like the NAND gate and NOR gate, and NOR gates are called universal gates because this NAND or NORs can be used or can be considered for designing any of the logic gates. And also we can see like if we want to implement this NAND gate by using different transistors like CMOS transistor, then it is easy to implement NAND gate than AND and OR gate. So this is easy to implement. So easy to implement using CMOS transistors or transistors. So that's why instead of AND or OR, we use NAND and NOR. But we can just see in the previous expressions that we have written for different functions, we have used and OR gates. Okay, so now we just want to see like how we can convert any AND or OR function and OR gate related function into NAND and NOR function. So that means here we are going to implement any function with the help of either NAND gate or with the help of NOR gate. Okay, so first of all we will be seeing the NAND implementation. So if we are going to implement the NAND gate means all the gates, all the respective gates are there. We should be able to implement all the gates with the help of NAND gate. So suppose an inverter is there that is going to do X inverted, that means X bar will be the output. So if this inverter can be implemented by the help of NAND gate, so that inverter can be implemented like if a NAND gate is there, if both the inputs of NAND gate is made equal, then here if we are putting X, then output will be X bar. That means now this NAND gate is able to work as an inverter. Okay. Similarly, suppose an AND gate is there. If we want to implement AND gate, we can put an NAND gate and then an inverter. And this inverter can be implemented by this. So we can see just like here, a NAND gate, whatever the output is coming, we have to again put a NAND gate with both the inputs. So here X, Y is there, so output will be X into Y. That is AND function. Similarly, if we want to implement OR gate with the help of NAND gate, we can implement that simply like whatever the NAND gate is there, before NAND gate we are able to put two NOT gates. Then we will be able to do the implementation of OR gate with the help of NAND gate. Or if NAND gate is there, we will be putting two inverters here. Okay, or we can just like write like here. This is one inverter, another inverter, and then putting it into the NAND. So this is your X, Y, the output will be X plus Y. So how we will be converting is just you can see if an AND invert logic is there, AND gate then invert. So that is three different inputs are there, X, Y, Z inverted. So this can be implemented with the help of inverted OR gate. So the similar function we can get by this like an OR gate is there. If all the inputs are inverted of an OR gate, we can get the similar structure X dot Y dot Z complement. That means if an OR gate is there, if all the inputs are being inverted, then this OR gate will be behaving like an NAND gate. Okay, NAND gate means AND plus invert. Okay, so I have got the I think you have got the point. Okay, now suppose this is a question. We have a function f that is represented by ab plus cd. So if any function is there that is represented in terms of, this is called like and followed by or. This is called and or logic. And or logic, or we can call it further, it is called two level logic. Two level logic means first we have done AND, then we are doing OR. So this is AND OR logic or two level logic. So if any function is there can be represented in terms of two level logic, then to convert a two level logic uh, function, we can follow these steps to convert it into either NAND or NOR logic implementation. So if we want to implement this one, so it is first of all we will be doing A and B AND, then C and D AND, and then together we will be doing the OR. So this is level 1, this is level 2, two level function is there. Okay, so now in that we know if we want to implement this AND with the help of NAND, we have to put an extra bubble here. Okay, so we have to put extra bubble, and to convert this AND to NAND, we have to put extra bubble, and also to minimize this extra bubble, we have to put another bubble in this path so that this bubble will be minimized. So NAND, it's like not and not will be minimized to the same value. Not and not will be minimized to same value. So we have put one bubble here, one bubble here, and one extra bubble here, and one bubble here. So we can see this is converted to NAND if we putting the bubble here and bubble here. So it has converted to NAND. Now to minimize this, to remove the effect of this bubble, we have to put another bubble here, suppose. So this bubbled OR is there. So bubbled OR is nothing but the NAND gate. So we have just seen previously, if bubbled OR is there, okay, so this is called invert OR, or call it bubbled OR will be equivalent to NAND gate. Okay, so here it is bubbled OR is there, so it will be nothing but the NAND gate. So we can just follow the further step. Next step is like this was already been converted to NAND, and now this will be replaced by NAND gate. So a two level gate realization was there, that is AB plus CD. Now this AB plus CD can be realized by using the NAND gate. So this is the NAND gate equivalent of F. So this is the NAND equivalent of F. So this is how we will be converting to NAND. So suppose another function is there. So this is the function we need to convert into write the circuit with the help of NAND gate. So this was the function. Okay, so here the function is given as the summation of mean terms. So if summation of mean terms are there, so now to minimize this function, we will be using the three variable k-map minimization. So with the help of three variable k-map minimization, we can just see. So 1, 2, 3, 4, 5, 7. So here 1 minterm 1, 2, 3, 4, 5, and 7 minterms are there. Now we will be doing the pairing. So pairing will be done with respect to, like, here one quad has been formed. Okay, so one quad is there, and these two are left. If these two are left, we have to make the pairing also. So here we will be doing one pairing, and this is another pairing. So with respect to that, we can see the function will be coming out to be here. So by this pairing, x y bar will be coming. By this quad, only z will be coming. With this term will be x bar y. So this was the function. So now this we have to implement. So this is a what is called and or logic. It is and or logic, or we can call it like it is a two level logic. Two level logic implementation, or it is nothing but the sum of product term. It is written in SOP form. So if this is the form, we can convert it, we can draw its circuit. So circuit will be this. So its circuit will be like x and y bar, then x bar y, then z is separately. Now together all will be so now all will be all together. This will be our function. This is z. So if this was the function, now we will be including we need to implement with the help of NAND gate. So we need to convert this AND into NAND. by putting a bubble. If we are putting a bubble here, we have to put a bubble here also. To implement this, we have to put a bubble here. So to compensate this bubble, we have to put another bubble here. Okay, but to convert this bubbled R to a NAND, we have to put another bubble here. So if we are putting a bubble here, we have to compensate with a NOT gate. So this is how this has been implemented, the same one. So if we are implementing this NOT can be implemented with the help of NAND gate easily. So now this has been converted NAND, and this is converted to NAND, and this was the NOT. So NOT has been included in this term only. Okay, so instead of Z, we have written Z bar. And if we want Z bar, we can convert this to a NAND gate by this logic. So it is Z, and this will be giving out the Z bar. Similarly, we can apply the similar concept here also and here also. So this is how we can convert a given function with the help of NAND gate. Okay, suppose another example is there. So this is the function with the help of NAND gate, and we need to draw the logic diagram. Okay, so this was the circuit function. So by this function, we need to use the K map. By using the K map, we can minimize this function, and this function will, after minimization, it will be coming out to be here. So if this is coming, we need to go with the two level representation. So by AND OR logic, we can implement this circuit like x bar, y bar, x, y, and then z, and then overall we will be going to OR it. So now to make it NAND, we have to put another NOT, one NOT, and here to make it NOT, we need to make it a NAND gate. We have to make another NOT here and another NOT here. So by this we will be implementing this. So now this will be converted to one NAND, and this is another NAND. So three NAND, and this is inverted like this will be Z. We will be making it. Okay. So that was the NAND implementation. Similar we can do with the NOR implementation. If we want to implement any given two level logic with the help of NOR gate, we can convert that. So if any x variable is there, we need to do the x bar. Then for NOR also, this is OR, into that this is NOR. So in that NOR, if both the inputs are same, then the output will be the NOR logic. Just we will draw like, if both inputs are same x, the output will be x bar. Similar is the here, if OR is there, OR, so in NOR we will be putting an inverter, it will be converting to a OR logic. If we want to convert to an AND logic, so if this is a NOR, into that if bubbled NOR is there, so bubbled NOR will be converted to AND logic. Okay, so this is like OR plus invert is there, OR gate plus invert, this is NOR. Similarly, if AND is there, if we are bubbling it, this is bubbled AND logic. See, this bubble and logic is nothing but the NOR logic. So similar concept we can use. So here an example is there. So if f is equals to written in, this is in product of some form. Okay, so it is written in product of some form. So to implement in terms of uh, NAND, in terms of NOR, we have to write it in terms of product of some form. So f is written in a plus b, c plus d, and e. So first of all, initially it will be implemented with, it is called product of sum is written like it is, and it is, so product of some form, it is written like or and logic. Or and logic means it is first of all ORing, then ANDing. It is or AND logic. So sum of product was AND OR logic. Product of sum was OR AND logic. It is also a two level logic. Also two level logic. So two level logic is nothing but we will be able to first in the first step we will be doing the OR, and the second step we will be doing the AND. Okay, so we can proceed with the implementation. So here a plus b, c plus d, and e. So a plus b will be doing first. So if a plus b will be doing with the OR gate, then c plus d with OR gate, and e will be ANDing it. So once we have done the ANDing, to make it NOR we will be putting the bubble. So here bubble, one bubble. So we can just start with like first this we can implement by like a plus b we need to do. So a b, so it is a plus b. Another one is c plus d, and then e. All will be AND. This is AND. This is your function. But we need to convert it into NOR. So to convert it into NOR, we will be putting extra OR, a NOT gate, another NOT gate, this NOT gate, this NOT gate. And to make it convert bubbled AND, we will be converted. So here an extra will be converted. So this will be a NOR, and this is already a NOR. So two NOR, and this is three NOR. Okay, so this was the implementation. Now we can proceed like we can convert it into the same. Okay, so now we can convert it into logic. So this will be nothing but a NOR gate. Okay, so suppose another implementation is there. If we have another function that is defined in terms of different three different stages. Okay, any other function is there that is defined in terms of three stages, we can convert that into the NOR also. So by putting the bubbling. Okay, so bubbled and convert to bubble and to a NOR, and OR is there. So by bubbling it on the output side, we will converting it into NOR. So this is how we can convert into a two-level minimization, or even the further multi-level minimization to NOR or NAND logic. This is another example. This is given. We need to implement it into with the help of NOR logic. So if we want to implement with the help of NOR logic, what we can do is we have to first do the implementation separately here. So it is a multi-level realization is there. Okay, so initially we will be writing here. So this is the first stage. So once we have converted it, now we need to implement with NOR logic. So we will be bubbling it. So bubbled AND will be NOR. So wherever there is AND, we will be bubbling it. And whenever there is OR, we have to put NOT here. So if we bubble here, we have to bubble here also. If we bubble here, we have to bubble here also. Okay, so this has been converted. Now we need to convert this also. So here we will be bubbling, then we will be making it dash. We will be bubbling, again we will be complementing, bubbling, complementing, bubbling, complementing. So its equivalent circuit will be like here. Or this is NOR, and here bubbling means it was initially W dash, now W. X dash was there, X will be there. Okay, so once you have done this, next step will be here. So we will be after bubbling, we will be removing this complemented form, and now this will be our original form that we will be getting. So with respect to that, we have converted AND or OR logic to an OR logic. So this is all about implementing any circuit with the help of NAND or NOR logic. So I hope you have got the point.